and see how that compares to the exponential. Okay. If we look at logarithmic functions are always written as y equals the log base b of x. That's actually equivalent to the expression the base raised to the power of y is equal to x. That was how we would pass between logs and exponentials. So just like before, we're going to build a table of values. We're going to, in this particular example, look at y equals the log base 2 of x. And let's refresh ourselves on how this all works. If I were to plug in 1/4, I'm finding the log base 2 of 1/4. So really the question I'm asking is 2 raised to what power will be 1/4? Well, 2 to the negative 2 is equal to 1/4. Similarly, if we plug in 1/2, the log base 2 of 1/2, 2 raised to what power is 1/2? That's right, negative 1. If we let x equal 1, the log base 2 of 1 is 0. If x is equal to 2, the log base 2 of 2 is 1, and so on, and so on, and so on. If we take a look at the x values go from 1/4 to 1/2 to 1 to 2. We're doubling the x values every single time. The effect on the y values increase by 1 every single time. If we actually look at the graph of an exponential function side by side with a logarithmic function, let's see if I can get that, what we'll actually notice is if we look at the x and the y values in the exponential, when x is 2, y was 4. Over here in the corresponding logarithmic, x is 4, y is 2. Let's do this for another point. In the exponential, if x is 4, the y value is 16. We go over here to the logarithmic function. If x is 16, the y value is 4. This is actually going to support the fact that the exponentials and the logarithmic functions are actually inverses of one another. Let's take a look at this on the graph. Alright, back to our friend Geometry Sketchpad. Over here, this graph, the red graph, is the graph of y equals 2 to the x power. We saw that before in a previous section. This graph over here is actually the graph for the log base 2 of x. In order to get the graph to show up, I actually had to use the change of base formula. Don't worry about that. Just know that this is what the graph of log base 2 of x is going to look like. We pointed out that in the data tables, these two graphs are actually inverses of one another. Another way to look at this is if we were to graph the line y equals x, which I've got up here on the screen, the graph of the exponential y equals 2 to the x actually can be reflected across the line y equals x to generate the graph of the log base 2 of x. Well, and now I've got some properties for the logarithmic functions that we're going to take a look at. Alright, here we go. So now what I've graphed is I've graphed a logarithmic function. What we saw in the last table of values is the x values actually as they double. So as we go from an x value of 1 to an x value of 2, I realize the numbers are small and you can't see them, to an x value of 4, to an x value of 8, as we go all the way out to an x value of 16, the y values, they are increasing, but they increase very, very slowly. As we get in closer to 0, never actually crossing the 0, the y values actually decrease down towards negative infinity. This red graph is the graph of the log base 2 of x. Because of some limitations with Sketchpad, I'm not actually able to type in log base 2 of x. What I needed to do is use the change of base formula, which is this natural log of x divided by natural log of 2. So let's graph log base 3 of x and see how that compares. So we go down to plot function, and we see now the blue graph. The blue graph is still increasing from 0 to infinity. It's intersecting the red graph at the point 1, 0. But the blue graph is actually below the red graph once they intersect. It is above the red graph over here. Well, let's graph log base 5 of x. As expected, log base 5 of x, this is the purple graph. It intersects the other ones at 1, 0, but this graph is actually below the blue graph and the red graph. What we're seeing is as the base increases, the graph increases slower every single time. So we're getting a graph that sort of plateaus and slowly increases. This next one would be the log base 1/2 of x. Now, in this case, what we actually see is the graph is decreasing as we go from 0 to infinity. If you play around with the rules for exponents, you can verify that that's true, but it also intersects at 1, 0. So let's summarize all this information in one nice table. All right, here's the last part. For all logarithmic functions written in the form y equals log base b of x, they're all going to pass through the point 1, 0. They're all going to have a vertical asymptote at x equals 0. What we saw in Geometry Sketchpad was if b is greater than 1, then the graph actually increased from left to right. For values of the base between 0 and 1, again, we don't let the base be 0 or negative. We also don't let the base be equal to 1. The graph will decrease from left to right. The domain for all of these was 0 to infinity, and the range was negative infinity to positive infinity. I hope this was helpful. In the next video segment, we're going to look at transformations of the logarithmic and exponential graphs. Good luck, Mavericks.